Okay, good. So in all presentations before, we were assuming that electrons, that orbitals have total momentum equals 0, which is a correct situation for isolated molecules surrounded by vacuum. And it is also a good approximation for insulator where band gap is bigger than 3 electron volts. But if we deal with metals, solids, any periodic materials, especially conjugated polymers, nanowires, thin films, then there are chances that orbitals have several replicas with different overall momentum. This overall momentum is recorded in the so-called K-points file, and this representation with momentum dispersion will need to compute couplings between not only different orbitals, but orbital, it can be same or different index of orbital, but it will be different value of momentum. For example, it can be transition from LUMO with non-zero momentum to LUMO with zero momentum, or LUMO plus one with non-zero momentum to LUMO with zero momentum, and several possible cross terms. The simplest model, class of models where this is needed are one-dimensional periodic systems like conjugated polymers. So Amir and Kea will eventually need it. Maybe not immediately, but it's a natural clientele. And the anyone who deals with periodic models with where there is no vacuum in either one of direction may need it. And one of the examples are a project that Boston is pursuing, two-dimensional thin film. And I think it is one of the projects that Steven is exploring at his free time. So thin film of a material which needs momentum dispersion in both directions. Sorry for the long introduction. Aaron, floor is yours. Your microphone seems muted.
Okay, there we go. So yeah, that's good because I didn't. So I figure since I'm going last, I didn't make a lot of slides because a lot of the procedure is redundant. So I guess Dimitri gave motivation for why momentum dispersion in periodic material, and I've thought of just providing two examples, which might be of interest. So momentum dispersion just means that your electrons can have various momenta. So your HOMO can have various different energies for its band, and that's what these black and red lines represent. So black's conduction and red is valence band. But in some materials, the lowest energy for the conduction band and the highest energy for the valence band are offset. And then that's generally called an indirect band gap. So they have different values of momentum. And the reason that that's important is because it adds another energetic barrier for processes like radiative and recombination. So you need energies which correspond to the band gap. So the vertical lines, but you also have to have enough energy momenta corresponding to the difference in the x-axis. So it makes the process much slower overall. And so on the left, I show silicon, which is like a prototypical example for an indirect band gap. And then in the near future, I'm planning on investigating, I can look at direct band gaps for perovskite materials for my future career. So I won't get into the heavy details, but for certain crystal structures, you can also find bands like this figure on the right give down or give new peaks in the absorption. So those are two examples of indirect band gap materials. And so it's just a general background for why we need momentum dispersions or include them into the non-adiabatic coupling calculations. So the first thing I'll go over is just generating a simple band structure from the DFT calculations. And so the initial step would be to do geometry optimization. And I guess there's some ambiguity of whether to only do it with one K point, which would correspond to like the K points file shown on the right, where there's just 1, 1, 1. I'm not sure if you included more K points, if that would drastically change your optimization. That's something that would need to be checked to make sure your structure's right.
Aaron, for geometry optimization, one needs to have at least 2 K points in each direction where there is a periodicity, and it may change the geometry. It's just a rule of thumb.
Okay.
If there is no periodicity, then it doesn't matter. But if it is flexible material or metal, then results may depend. So two is safer.
Okay, so optimize with 2 K points, and I put the 2 into the Z direction because that was the direction that the model is periodic that I initially tried this on. And so if you optimize the geometry and then to generate the band structure, you just create a subdirectory with your structures and all your input files. Then you just increase the number of sampling points in your K point file. And depending on how fine you want the results to be, you have to increase or decrease this number. So for this example, I chose 8. It gives the band structure, which is shown on the right. And you can see that for some of the structures, you can see kinks into them, so they're not very smooth. So like this green line kind of looks like a line going from this segment and then kind of kinks to fatter. So to make that a more smoother line, I'd have to redo the calculation with more K points, increase this to like 16 or 32. And then there is a general instructions on how to plot dispersion. This advice.dispersion.v10. General instructions on how to generate this plot. And that's a lot of the time would just be figuring out like the right amount of K points that you want for the dynamics, because to get very smooth curves, you need a lot of K points. But for doing dynamics, it's kind of a balancing act between like how many points you want to look at, because if you do 32, or if you sample 32 K points, that means you have to essentially compute 32 sets of couplings, which can get very cumbersome. So you kind of have to find the right balance between sampling points and how like a coarse-grained band structure compares to the very smooth one. So once you figure out how many cables you want to run, you do all the same machinery that's been described by Amir, Yule, and David. So you get your structures from the MD directory, so all your position files, pop, car, the K points, in car, and input overlap. And then the scripts which compute the indirect couplings are these indirect overlap.exe and overlap.exe. And those are located in the bin k-os directory in the bin. And the general Fortran scripts resided in there as well. So if you need to make changes, like the maximum number of K points and like other parameters to get the script to run healthily, you can copy those to your working directory and update them there. So once you get the jobs running healthily, you will, I guess there's two sets of couplings that you'll get. So you'll get the direct trans, which are labeled as one dot number. So the 1.01 refers to direct transition from 1 to 1. So there's no change in momentum. And then the last digit corresponds to the time step or the structure that the calculation was done on. And then there are also indirect transitions, which represent a change in momentum. And one has a slightly different name. So coupling.01.04.number would represent the coupling corresponding to the changing going from K.1 to K.4. And then the N number just refers to the time step again. And yeah, I guess that's all I have to show.
Okay, please join me thanking Aaron. So, any questions in the chat line or verbally?
I have a question, Aaron.
Please do.
All those direct and indirect transition files will be generated at the same time after running that SH file?
I believe so. So I haven't done the calculations myself yet. I was browsing around in a direct where the couplings were computed healthily, and the way that that author computed them is there was two separate directories. So they made one. So it seems like they had one script that computes the direct transitions, and then in a separate directory, they computed the indirect transitions. So it's possible to do them all at one time.
But they all generated at once.
They are
into separate directory, Dr. Kilin, or no?
Yes, same way as you explained for up and down.
Oh, okay.
The script is running and populating different directories with coupling files.
I have another question.
Mm-hmm.
If you change the number of key points for the momentum dispersion, where should we adjust the script for doing some coupling calculation? Is it automatic or no? We need to modify that.
so if you if you change your K points file to like a amount of K points on one direct, so that would change the file that change like the size of the wave car. And so you might have to change the Fortran script to read in like the amount of K points that are in the wave car. Because sometimes like because with Fortran scripts you have to tell, you have to like they say how like what's the max number of K points to read in. And if the wave car has like 10 K points, but the script is told only to read in 8, there'll be an error.
So which script should be modified? I didn't get that.
So the Fortran. So
can you go back to previous slide? Did you list that script here?
No, so that was what JobEd was showing.
Okay.
Some version of it anyway.
So the newer version of the script is in development and will be released soon, which will automatically read number of key points, but it is too early. The version that Aaron is showing has it was tailored for like 4 K points as a to make some quick investigation, because number of as soon as we have more than 1 K points, it multiplies number of orbitals by number of K points. For example, if you have like 10 orbitals with 4 K points, it will be 40 orbitals, and for transitions you have 40 by 40. So it escalates pretty much substantially.
Okay, thank you.
More questions to Aaron? More questions, one?
Oh, okay, let me ask
please do.
So, for instance, for my system, I have a conjugated polymer, a 1D periodic model. So, do you suggest I should always do the momentum dispersion coupling?
No. It will be if you have enough energy and interest, it will be maybe your theoretical paper number 4. Try to do one gamma point only, because it will be a lot of new information, and it just you will lose enthusiasm by facing several challenges. So let's do one thing at a time.
No spin calculations.
Scientifically, it is interesting, promising, and beneficial to explore momentum dynamics with momentum dispersion for your model. But even without K points, it will be sufficiently novel to be competitive and publishable. And probably you should try without K points first, and then plan K points dependence as a next step.
And for sure, momentum dispersion should be much more expensive computationally, right?
Right.
Okay, thank you.
So you're welcome to try, but it would be not prudent to put all efforts and think of next paper as momentum dispersion, because it will take some time and some path of success and failures.
Okay, thank you.
So if there are no more